Thank you. Okay, I've opened the room up now.
It seems like host disabled participant screen sharing.
Okay, let me see what I can do there. I need to get tech support because normally there's a security tab that allows me to adjust who can share screen, but I'm not seeing that right now, unfortunately. Okay, so I can change this. Who can start sharing? Panelists. Okay. Are you able to share now?
Yes, can you see my PowerPoint?
Yeah. It's Farah. Is it Farah or Farah?
Farah is good, thanks.
Farah. Okay.
Yeah.
So I'm going to get started. And first, apologies for people joining a bit late. We had an issue with the host not making it on time, so I've kind of taken over as a stand-in host, but I haven't received host training, so I'm doing my best. I'm supposed to be the moderator of today's session, however, so I am in the right place. My name is Steve Farber. I'm a professor here at U of T, and I'm very delighted to be the moderator of this panel. And I'm going to go off script for the sake of time, because I believe a lot of you have been on some of these sessions already. But the general idea is that we will have 6 minutes per presentation. At 5 minutes, I'll quickly give you a 1 minute warning, wrap up. And if you go over 6 minutes by 30 seconds, you get a ruder interruption, and we need to go on with the next conversation after that. I've been told that the chat and Q&A in this session is kind of reserved for technical challenges, and I hope that Willem is here on the call to help with any of that as it comes up. And if you look back to the interactive program, there's a URL, a link to kind of a Q&A document where people can keep track of questions, and towards the end of the session, even with this slight delay in getting started, we might be able to get to some interactive Q&A. So with that in mind, I'd like to welcome our first presenter, Farah Machlab, to begin your presentation. And everyone else on the call, please do mute yourselves until it's your turn to present. Thank you.
All right, thank you. I'm Farah Machlab. I'm an associate at IBI Group. Today I'll be presenting about transit performance. This is a system that uses GTFS and GTFS-realtime to record and measure service performance in real time. It measures performance from two perspectives: the quality of service provided by the agency and the quality of service experienced by customers. So a little history about the system. The MBTA in Boston engaged us about 6 years ago to find a solution for automating their daily report for subway performance, which is what you see here on the right. The method in place at that time was very manual and very time consuming. It used exports of the timetable and track circuit occupancy information from their train control system and used Excel as the front end for producing the report, often with a few days lag. So at the time, MBTA was already generating their data using GTFS and GTFS real-time formats. So the question became, could we leverage the open data produced using these standards to meet the following objectives? So we wanted to remove the dependency on these proprietary extracts from the train control system, or in the future from BusCat-AVL for bus performance. We wanted to automate the entire process. We wanted to be able to extend it to other modes such as light rail and commuter rail. We wanted to provide output that used the GTFS identifiers. And we also wanted to provide a customer-centered performance perspective and do all of this in real time. So this is the system that we developed. It's called Transit Performance. And this here shows a schematic of the system and the flow of data. So the system reads in information from the GTFS feed and the GTFS real-time vehicle positions, trip updates, and service alerts feeds, which are generated by one or more agency systems. From the GTFS, we capture the scheduled service for the day we're processing and use that as a benchmark to compare actual service. From the vehicle positions feed, we capture and infer arrival and departure times at stops. And then from these arrival and departure times, we can calculate travel times, headways, and dwell times. From the trip updates feed, we record all the predicted arrival and departure times. And from the service alerts feed, we have incident and disruption information available to us. With all this set of information, we can then calculate and measure a wide range of performance metrics that you see listed here. For example, schedule adherence, headway adherence, etc. The system is also set up to ingest passenger arrival rates, which allows us to weight metrics by the number of passengers affected to get customer-centric measures, such as passenger wait times and passenger travel times. So all of this is done in SQL Server and recorded in tables in the databases, which the agency has access to, and they can run their own SQL queries. We also have a number of APIs available for customers and third-party developers. So just a little more detail about how the daily processing in the system works. At the beginning of the day, the system checks for and loads the latest GTFS and any configuration files if they've changed from the previous day. And then it creates a schedule for the current day and uses it to set up benchmarks for service. Throughout the day, as service is being operated, the system downloads and processes the GTFS real-time feeds. This happens every 5 to 30 seconds, depending on the process. And then we can calculate in real time the actual headways, actual travel times, dwell, schedule adherence, etc. Every 5 minutes, we combine the operational data with passenger loading data and calculate and generate metrics for the past hour and the current day so far. And finally, at the end of the service day, we reprocess the entire day, clean up the data, generate daily metrics, write to historical tables, and archive data. So who are the users of the system and what types of analyses can be performed using the data generated by the system? So it's used by operations management to monitor operations in real time and for the previous day. It's used by service planning to identify issues with specific routes or segments and make changes to improve performance. It's used by management to understand performance of the system at a high level. It's used by customers to understand how their routes perform that they take personally, and the APIs that we provide are used by developers for third-party applications. So the transit performance system powers a portion of the MBT's public-facing dashboard, MBT Back on Track, which you see here in the upper right. And the disaggregate and the historical data that's been collected. Okay, the disaggregate and the historical data that's been collected by the system since 2015 is also very powerful for conducting a wide range of studies, such as level of service analyses, runtime model configuration and analyses, dwell time and berthing analyses, and intersection delay and traffic signal priority benefit analysis. We're continuously adding new functionality and making improvements to the system. And so the following features are currently in development or testing with the aim of adding them to production by the end of the year. So adding a new metric, integrating with service alerts to see how they affect performance, integrating with other data sources such as ATC, and measuring the quality of the vehicle location feed. And so the system is open source. At the link here, we encourage you to play around with it, collaborate, add improvements to the system, and thank you.
Thanks so much, Farah. That's great and right on time. So at this point, can I please invite our next presenter, Nicholas, to share your screen? And can we just test your audio quickly before you begin?
Yeah, hey, can you hear me?
Yes, it's perfect. So I'll start your timer when you get going with your slideshow.
Okay, great. Thanks. So my name is Nick Caros. I'm a graduate student at the MIT Transit Lab, and I'm presenting a project that's been developed over the last year or so with several collaborators who I'd like to acknowledge: Xiaotong, Anson, Stewart, John Attanucci, and Jinhua, Zhao. And I apologize, this is going to be a very Boston-focused start to the session this morning. You'll have to bear with me. So what we're trying to do here is develop a visualization dashboard similar to the one that you just saw, but this is more focused on historical data for different types of analyses. And the motivation for this project, there's a ton of transit data that's being automatically collected by transit agencies. And we want to make sure that you can use this data to generate insights that don't just happen based on ad hoc queries, that only certain people within the agency are able to do. So we want to create a user-friendly interface in order to look at some of this past performance data. We wanted to emphasize a quick, intuitive, and flexible filtering so that if you discover something that you didn't expect in the data trends, you'd be able to dig in deeper with just a few clicks. And then the visualization component is really important to us as well. We want to make sure that people can identify trends that are occurring spatially, which is a little bit more aligned with how passengers experience the transit performance. And one thing I wanted to point out on the right-hand side is often you'll see transit data presented in a tabular format, which doesn't really give you the kind of insight that you might get from a visualization dashboard. And so the design of our dashboard, we wanted to emphasize an open source tool that doesn't rely on any particular conventions, and then that way it would be generalizable for any transit agency. We do have to use custom scripts to collect the APC AVL data because of the different vendor data formats. But other than that, the entire framework is set up so that it doesn't rely on any GTFS conventions and it doesn't rely on any proprietary software. And one thing that we're also doing with this is generating the geometries for the different bus routes using the GTFS feed and OpenStreetMap. And some of the key features of this tool, we have quite a large number of metrics. Some of these are vehicle focused, so things like frequency, speed. Some other ones are more passenger focused, load, crowding, excess wait time, things like that. And also some productivity based performance metrics as well, like revenue hours. This tool allows you to visualize any metric at different levels. So you can look at just the route level or down to the stop-to-stop segment level, or even at the corridor level if there are segments that are served by several different bus routes. We include a custom time range filter, so you can look at the half-hour resolution for any particular metric that you're interested in. And then we allow filtering by route, direction, and metric values. So if you only wanted to look at the bus segments where the crowding is, say, over 50% of the seated capacity of the bus, you can filter down, and you can do all these things simultaneously as well. We allow toggling between the median and the worst decile in case you're only concerned about particularly bad performing bus routes. And one of the great features of this tool, I think, is that you can click on any route or any segment, and then it'll pull up additional information. And I'll show you that in just a minute. And then finally, it allows for the data selection to be exported to a CSV table. And that only includes the data that you filter down to. So this way, that can be exported for additional analysis. And so this is what the tool interface looks like. You'll see on the left-hand side, there's a dynamic legend that shows you what the different colors mean. And then it also gives you a readout of all of the current filter states. Because there are so many metrics and so many different ways to filter down this data, this allows you to quickly see what it is that you've filtered to in case you're playing around with a number of different settings. And in the center, you see the actual map itself. And this is an example of how you can click on the different routes to take a look at the performance metrics. It also gives you the first stop and the last stop of that particular segment and some more information there. And on the right-hand side is the general user interface. And what you can do here is select different routes. You can also, there's a select all option, and you can do a multi-select as well, and then apply the different filters that you're interested in. And you can see the filters down the right-hand, bottom right-hand corner, where you can start to filter by the different metrics. So some of the examples of ways you could use this tool, an instant review of all the metrics for a particular segment. So for example, if there was an upcoming detour required, you could take a look, quickly look at the historical runtime, the delay, the passenger boardings at the location of that detour in order to understand what the impact might be. And then you can export that to share with your other agency partners that might be interested. You can also take a look at high potential transit priority locations. So if you were interested in potentially introducing some new queue jump lanes, you could quickly take a look at a very kind of high level analysis of where there's high ridership combined with low speeds, where you might be able to get some benefit from those transit
1 minute
priorities.
warning.
Thanks. And then of course, there's some applications here for the COVID-19 response where you can locate segments where crowding is particularly high, especially if there's flexible service delivery happening. That might help to inform any kind of future service planning to reduce that crowding. And going forward, we have a few items on our agenda going into the fall semester. One of the things we'd like to do is allow comparison between 2 different time periods, so you can see temporally how things are changing over time. Another one is to automate some of these analyses, so that high potential transit intervention analysis that I just mentioned as a use case. We'd like to build that into a configuration file where you'd be able to just click one button and produce automated reports. And then finally, we'd like to create a sort of a journey explorer tool where we'd envision this being that you would click on a segment, for example, and it would show you exactly where everyone started their journeys, when they're traveling through that segment, and where their journeys are planning to end, so long as you have this origin destination data available to you. So similar to what's being shown on the right here, but snap to the actual transit network, so you can understand how different journeys might be impacted by disruption to service at a particular segment. And that's it for me. Thank you very much.
Thanks very much, Nick. That's great. The next speaker today for the paper, Who is Complaining the Most? Combining Bus Operational Data with Customer Complaints in Portland, Oregon. I believe we have Leila Hawa here to present. Leila,
Hey.
hi. Yeah, your audio sounds great. Can you just go ahead and try sharing your screen?
Yeah, for sure.
Okay, it looks great, and you can go ahead.
All right. Hello, my name is Leila Hawa, and I'm excited to present to you, Does the Squeaky Wheel Get the Complaint? Linking bus performance, socio-demographic characteristics, and customer comments. Transit agencies rely on service performance measures to guide service improvements. They also collect customer feedback on performance to measure level of satisfaction. However, these 2 sources of feedback are often handled by different dedicated departments, and the data is rarely linked. Linking the 2 could generate more targeted operation strategies that are more responsive to public needs. So with this in mind, we conducted a study linking AVL and APC data and complaints data from Portland, Oregon's TriMet. Our 2 research questions were, do bus routes with more operational issues measured by on-time performance have more service complaints while controlling for the number of passengers? And also, does the level of affluence of a neighborhood that a bus serves impact the number of complaints while controlling for on-time performance and passenger demand? So our study period took place from August 2018 to January 2019 and included 82 regular bus routes, as well as a total of 1,530 service complaints that were further subcategorized into different types of service complaints. It also included 40.1 million observations in the AVL and APC data. And our 3rd source of data was census data for the socio-demographics. And using that, we generated a vulnerability index as well as the average median income for each bus route. For the analysis, we used service, complaints, and service area socio-demographic attributes to rank the top 20 TriMet bus routes, so 3 separate rankings. And then, since that's ranking analysis is a bit more exploratory, we generated a series of logic regression models to quantify the relationships. So here's an example of one of the ranking tables. This is by on-time performance. And here you can see like the 20 worst routes by mean late on-time performance aren't actually the ones with the highest complaints. So that's pretty notable. And this is a summary of the 3 rankings. So this is by all 3 different rankings. And notably, you can see that bus routes with the most complaints per ridership were very early over here compared to the other 2 rankings. Additionally, bus routes that are late most often have more complaints when controlling for ridership than routes with the most ridership over here. Lastly, over here, you can see that routes with the highest ridership also had the comparatively lowest median income. And here are our regression results. So we generated models at the route stop level, and they each had 9,338 observations. And the way that logistic regression models work is that it shows how much each variable increases the odds of a complaint. So in the first model, it was looking at any type of service complaint, but in the other 3, it was specific types of service complaints. And over here, you can see a variety of different service measures that we included, as well as if the bus route was a frequent service route, and also the route average vulnerability index. So for example, over here, you can see that like early on-time performance increases the odds of a deviation from schedule complaint by 47 times, all else constant. So our main conclusions were from the ranking tables that worse late on-time performance doesn't necessarily lead to more service complaints. From our regression analysis, we found that the odds of there being a service-related complaint was found to increase with an increase in the vulnerability index of the area surrounding the route, all else constant. So assuming that the population living along the bus routes also constitutes the ridership for those routes, then this could suggest that feedback from disadvantaged populations is not suppressed. So that's very interesting. We also found that if a bus has a high proportion of trips that depart early, then that could increase the odds of a service-related complaint happening, even more so than late on-time performance. And that could be because like a customer could potentially miss a bus if the bus departs early. So that kind of makes sense, but it's pretty interesting nonetheless. And lastly, we also found that bus routes that pass through areas with more vulnerable populations have higher odds of receiving a reckless driving complaint. So counterintuitively, more vulnerable populations could be more likely to voice a concern about reckless driving than less vulnerable populations. This could be because vulnerabilities tend to be co-occurring. So economic disadvantage, which is what we measure with the vulnerability index, could also exist alongside physical disabilities. Also, it could be indicative of poorer physical conditions, for example, poor road infrastructure in areas that are also more vulnerable. And our last major finding was that if a bus route was a frequent service route, that also increased the odds of a service-related complaint, especially for passive complaints. So that could potentially indicate that riders have higher expectations for frequent bus routes, frequent service bus routes rather. And yeah, thank you so much. If you have any questions, let me know. This is also my email. And yeah, thanks so much.
Hey, great job, Leila. Thanks so much.
Thank you.
Our next presenter submitted a video to present. So Willem, if you're here, could you please go ahead and share the video with the group?
Sure can, just stand by.
I'm assuming you won't need me to time this one, is that right?
I would hope not. No, it's a 6-minute video, so.
Okay.
Oof.
Hello, my name is Tianwei. First, I would like to thank my supervisor, Professor Mark Hickman, another student, Alexis, who also was involved in this project, and TransLink, who provided all the data. Managers of public transport services face the continued challenge of meeting customer service expectations. It is very important to understand the general nature of the empirical relationships between customer satisfaction and objective network performance measures. TransLink is the public transit agency for Southeast Queensland. It has recently redesigned its customer satisfaction survey to ask customers about the specific trip they made on a specific date on a specific route. These can be connected with both real-time data on the trip, including on-time performance, crowding, and in-vehicle travel time. The goal of this research is to provide some quantitative evidence on what potential operational improvements may in turn lead to the most effective gains in customer satisfaction. This knowledge would provide the evidence to support investments and achieve the desired user benefits and strategic outcomes. TransLink provided us with the customer satisfaction survey data from July to September 2019 with 70,367 survey cases. After a specific journey, a survey is sent to the registered passenger's email asking about the satisfaction level to different elements in the transport network, and people have to choose between level 1 to level 5. For reference to a specific passenger trip, TransLink provided access to Go Card transactions from July to September 2019, which records passengers' mode and route of travel, their boarding and alighting time, and the boarding and alighting stops, and similar information on any transfers made during the journey. A separate data set called Bus Arrival Data for July to September 2019 recorded the scheduled and actual travel time from one stop to another for every trip, for every route. In the TransLink bus network, this dataset also recorded the number of passengers boarding and alighting at each stop, and hence we calculate the number on board between two stops on the route. These three datasets are matched by common attributes, including date, boarding time, boarding and alighting stop, route, and direction. We only have the arrival data for bus, which is about half of the satisfaction surveys. About 70% of the bus survey cases can be matched with 5,244 Go Card transactions. We are able to calculate the on-time performance, which is the boarding delay, the difference between the scheduled and actual journey time, the load at boarding, and the maximum load during the journey. We use the ontologic model incorporating those objective variables to influence 4 specific elements from the customer satisfaction survey: the overall satisfaction to the specific trip, and the satisfaction to punctuality, the journey time, and the availability of seating. We calculate the marginal effect for each variable, which means how much a unit change in the objective performance variable will change the satisfaction. For example, if the bus arrives 1 minute earlier, the overall satisfaction score will be increased by 0.0052, and the satisfaction to punctuality will be dramatically increased by 0.0262. It means the improvements in on-time performance at the boarding stop will be more effective compared to similar improvements in journey time. In terms of passengers on board, the marginal effect is the improvement of satisfaction score by reducing one person on board. The passengers on board are more associated with the satisfaction with the journey time and availability of seating. With this information, we can probably predict the customer satisfaction after such objective improvement. This is just the objective metrics from a specific journey associated with the survey. We are also interested in the effect of previous journeys. The question is there a cumulative effect of objective performance on satisfaction with a given journey? To do this for each person, we extract all the historical transactions from the Go Card data and calculate those objective variables. We took samples from all the transactions. Since most of them are infrequent users, we take 5 trips prior to the survey trip for each person. We calculated the mean and standard deviation of these objective performance variables. Mean is the average performance of those historical trips, and the standard deviation captures the consistency of the performance of the 5 trips. Here we listed all the significant variables for each satisfaction element. It is interesting to notice that the standard deviation of the journey time is significant to all elements. So we should improve the consistency of the journey time to increase the customer satisfaction. Other variables, such as the average and the standard deviation of the maximum load, will also influence the satisfaction level to lesser degrees. This shows that the previous experience does have a substantial effect on the satisfaction of your future journeys. 2 major conclusions can be drawn from this research. First, the objective performance matrix variables will also influence the customer satisfaction to different elements to varying degrees. From looking at those marginal improvements, the improvement in on-time performance and the maximum load during the journey will give the most efficient gain. Second, it will assume that the average journey time performance and the consistency of the journey time performance will have the strongest effect on customer satisfaction for the future journey. Finally, I have some recommendations. We should definitely apply the model to a large data set as long as we have more service responses. We can also try to add random coefficients to the regression models to model taste variation. We should also do research on how to get objective matrix from real and ferry services because we currently have only the arrival data for bus. For other services, the tap on and tap off happens when people enter the station. It is very hard to get the on-time performance data directly from the real and ferry data. That's all for me. Thanks.
Okay, fantastic. And thanks to you virtually, wherever you may be, maybe asleep. Our next presenter is Menno Yap. And Menno, could you go ahead and share your screen?
Yeah, sure.
And yeah, your audio sounds good as well. So I can just start the timer as soon as you get going with your presentation.
Yeah, sure. How does this look like?
Yeah, it's good. I think just
Good.
hit F5 to,
Yeah.
because we're seeing your view, not the presentation.
Sure. Right.
Yeah, that's great.
Perfect. Hi, everyone. Thank you for tuning in. My name is Menno Yap. I'm working as researcher at the Smart Public Transport Lab of the TU Delft in the Netherlands. I'm also working at TfL, Transport for London, as public transport modeler in the UK. And the presentation today will be also on behalf of Odette Katz of the TU Delft. So I guess, at least in pre-COVID times, crowding and overcrowding in metro systems is quite well known. Many cities worldwide experience that. And there are also quite some studies in the past focusing on estimating how passengers perceive onboard crowding. So basically estimating a crowding in vehicle time multiplier as function of the crowding level on board. You have quite some stated preference research in the past looking at that, and more recently you also see some revealed preference studies applied to Singapore, Hong Kong, and the Netherlands. And these revealed preference studies basically try to use observed route choice inferred from AFC data to estimate how passengers incorporate their crowding perception in their route choice. And the work I'm presenting today is basically a follow-up on that work stream. We use a revealed preference approach as well, with the objective here to estimate how passengers perceive platform wait time after being denied boarding due to overcrowding in a metro network. So as input for this, we use AFC data. For a metro network, that's typically gate line, tap in, tap out data. We have AVL data, the train movement data. We also have a passenger to train assignment model, basically assigning the individual passengers from the AFC data to individual trains. And I guess the challenge of this particular work is not so much in the model estimation, as we use a rather simple model there. I guess the interesting part is more the choice set selection, to come up with some rules to determine which choice set is capable of allowing us to estimate denied boarding perception. So we have a couple of choice set selection criteria. Of course, for a given origin-destination pair, there should be at least two different observed routes. And with different routes, we mean they have to be physically different, because we, meaning you have a different platform or different stop, with the idea that passengers should decide on beforehand on their route A or route B based on their expected travel times, transfers, and also denied boarding probability. Of course, at least one of the two routes should have a substantial probability on denied boarding at either the first boarding stop or at the transfer location. In our study, we used 40% as a minimum threshold here. And here we define denied boarding as passengers arriving at the platform, but not boarding the first train departing from that platform after this arrival time, whilst this train had an occupancy of at least 75% of the crush capacity. There should also be no dominance, of course, and we are looking for journeys where there is an explicit trade-off between journey time and denied boarding. So one route should have a shorter journey time, but a higher denied boarding probability, and the other route a longer journey time and no or lower denied boarding probability. We used a simple multinomial logit model where you can see the utility function on the screen. And so effectively, the first component shows the initial waiting time for the first arriving train. And the second component shows the probability on denied boarding multiplied with the additional waiting time in case someone is denied boarding. So effectively, this reflects the expected additional waiting time due to overcrowding. We have the in-vehicle time as the third component, the number of transfers, and the path side logit to correct for overlap. We applied our method to the metro network of Washington, D.C. We used September 2017, Monday to Thursday data with the idea that crowding levels are highest in this particular period and these days. We focused on 15 minutes time intervals with our idea that this is the smallest time interval passengers can reasonably have some idea about denied boarding probabilities for a certain route. And applying all these selection criteria, we ended up with 11 OD pairs and 15-minute time intervals, which satisfied all the criteria. So in the end, we had about 800 observed route choices based on which we estimate a discrete choice model using maximum likelihood estimation. Looking at some results of our model, at the high-end level, you see that the rho square and the adjusted rho square are pretty high, above 0.8. Of the 5 coefficients, 3 are clearly significant and 2 have a p-value somewhat higher than our standard threshold. If you scale these coefficients to the in-vehicle time, as we've done in the figure below, you can see, for example, that a transfer is perceived as about 3.2 minutes in-vehicle time, but you can also see that 1 minute initial waiting time, so the waiting time for the first arriving train, is perceived as about 1.32 minutes in-vehicle time. However, if you look at waiting time perceived after being denied boarding, this value goes up to 1.83. So effectively, 1 minute waiting after denied boarding is perceived as 1.83 minute in-vehicle time. So this shows us that waiting time after denied boarding is perceived about 40% more negative than waiting time for the first train. In terms of policy implications, these values can help us in improving the quantification of impacts of overcrowding, denied boarding, for example, during pipeline disruptions, or in a cost-benefit analysis. It can also help us improve public transport assignment models if we incorporate this, and potentially improve the model accuracy. And I guess if you look at more future work we're planning to do here, is also incorporating onboard crowding in our utility function, and also testing a couple of different model types such as mixed logit and latent class. But that's ongoing work for now. Thank you for your attention.
That was great. Thank you, Menno. Very interesting figures coming out of that and useful to a lot of people here. Could we queue up the next presenter? It's Simon Kochberg.
Hi, are you able to see my screen?
Not yet, Simon.
I had to click share.
Okay, and now you're in. And before we get going, I just wanted to do a bit of an announcement that the Union Station website is live again, and sorry for those technical difficulties. And also a reminder to please leave questions for the presenters in the Google Sheet. I believe you have access to some chats. I left you the link there. It's also Union Station, and then the presenters will be answering questions that appear on that sheet in their own time. So please, we do encourage some interaction in that way in this conference. Thank you. And Simon, you can go ahead.
All right. Hi, good morning from San Francisco. My name is Simon Hochberg, and I work at the SFMTA. My presentation is going to focus on an in-house web-based software tool that we developed that allows agency staff to record in real time whenever an elevator goes out of service, which allows us to better communicate the current status of all 21 elevators in our light rail system. The Muni Metro light rail system has 8 underground stations, each with anywhere between 2 to 4 elevators, and many passengers depend on functioning elevators in order to use our rail system. But prior to our design and tool building process, it was challenging for riders to get current information about elevator status. When an elevator went out of service, the previous process was for the station agent to write the elevator on the out of service elevator's whiteboard in their booth, and then kick off a phone tree to inform every station agent at every station and ask them to update their own out of service elevator's whiteboard. The original station agent would then call and report the outage to the city's 311 system. This process is cumbersome, both for the station agents tasked with providing the information and for the transit riders trying to determine whether or not their stop will be accessible. And to address this, we adopted a user-centered design process. So user-centered design, to paraphrase the design firm IDEO, is rooted in the idea that the people who best know how to solve a problem are the people that have to face it every day. In the case of elevator status information, that meant we started by working with both the transit riders and the station agents. Our design process was iterative. We would build a version of the tool only to find that it wasn't technologically viable in our stations or that the riders didn't feel like the information they were getting was reliable. And then about once a week, I'd hop on the subway and I would meet with the station agents and collect their feedback on the newest iteration and grab their suggestions for improvements. This user-centered design approach meant that when it came time to roll out the tool for actual use, we already had the buy-in that we needed from users to make it successful. And this is the result. It's a remarkably simple web page built in HTML, CSS, and JavaScript with a little basic PHP to handle the connection to the database. You can see a table in the bottom part of the main panel where each row represents an elevator at a given station, and we're looking at the church station here. The status of that elevator is given in the table, as is the time at which the status for that elevator was last modified. Each station in our system has a page like this, and those other pages can be navigated to using the bar on the left-hand side of the screen. If a user wanted to change the status of an elevator, they could do so easily by clicking the update button at the right of each elevator's row, and that opens this modal, where they'd be able to enter the estimated time of repair and add any other comments before clicking on one of the 2 large in-service or out-of-service buttons at the top of the pop-up. And that's it. With that simple interaction, the real-time status of the elevator is updated, and that change is immediately reflected across our customer information systems. Again, our goal wasn't to generate copious amounts of data, but it was to make it as simple and as quick as possible to update the status of an elevator and get this vital information out to the riders that need it. This tool powers the publicly accessible agency elevator status page shown here on the left. And hopefully someday we'll be able to connect the data in this database to other applications such as trip planning apps. When rail service resumes in San Francisco at the end of this month and our subway stations reopen, our platform signs will show for the first time real-time elevator status, in particular at stations where transfers require changing from the subway to the surface. And all this is made possible by the data captured in this basic tool. We've also found that the tool is used in ways that we don't expect. So in the photo on the right, you can see that the station agent has turned their second monitor towards passengers and is displaying the elevator status to the public right from the tool. And we weren't anticipating it to be used this way, but it's yet another way that makes this information easier for our riders to access and to understand. So a handful of key learnings came out of this process. We worked really hard to ensure that the result was as easy as possible in these 4 key areas. Above all else, what we created had to be easy to use so that station agents, who are responsible for everything that goes on in a subway station, didn't see their workloads increase while recording this information. This tool had to make their jobs easier and had to do so immediately. Easy to explain means that the information this tool was producing had to be understandable without much effort. We debated making it more complex and trying to capture other types of data, but ultimately we opted to keep things as simple as possible so there was never any confusion as to what the purpose of the tool was or what the data meant. The tool had to be easy to build. Like any transportation planners, we have a number of other responsibilities and we're not software engineers or designers. So our goal was to build a simple tool that demonstrates the benefits of incorporating technology into what would have been a manual process. And to do that, we needed something that we could build easily and quickly and then move on from. Once we and our end users were satisfied with the product, we handed off ownership of the tool to SFMTA's IT department. And As we did so, we made sure that what we were giving them was fully thought out and, to the fourth point, easy to maintain. The simplicity of this tool has contributed to its stability. It hasn't gone down once in the nearly 2 years since it was released, and that's more than we can say for a lot of our systems. In conclusion, by adopting a user-centered design approach and by striving to meet these 4 easy goals, we were able to meet the needs of our users, craft a simple solution to what was a complicated and cumbersome process, and make real-time elevator status information available for the first time to our riders. Thank you very much.
Thanks, Simon. That's great. And thanks to all of our presenters here today. We've got only 5 minutes left, so I'll do a little bit of a question and then open the floor to any of our panelists to answer, and that will probably take us right to our lunch break at noon. Again, sorry for the technical difficulties that we had in this session. So I think one of the really amazing things coming out of these presentations is the use of real-time transit data to have a much better understanding and kind of a universal understanding about the potential experiences of customers on the networks. I think that that's like a vital step towards really trying to understand also some of the social implications and differences in the distribution of performance levels experienced by different types of passengers. And a lot of the systems that are generated here, my critique is that, especially from the first few presentations, they're generated with kind of an atomic customer in mind, a rider, more or less a rider without any attributes associated with them. And I'm just wondering, to what extent do you see the possibility for building on these existing tools in order to incorporate user information like age, income, ethnicity, things that social scientists or planners might use to understand equity and justice concerns in the transit system? And I guess the follow-up is, should we be thinking about adding that information on to these existing systems that you're developing, or would these systems look very differently if we were trying to incorporate that information from the ground up into our methods and tools? So I'll just open that up to any of the panelists who want to respond.
Well, I could maybe add a bit to that, Steve, although my presentation was not really focused on the dashboards and stuff like that. What I think is probably very interesting, and maybe it was already in a few of the presentations we saw this morning, is moving a bit away from the, I would say, train statistics or vehicle statistics to the passenger statistics. So it's great to know that a train was on time or not, but I think it's even more important if we could show journey delays for particular origin destination pairs or different boroughs or different parts of the city. So I think that would be, for me, from a sort of passenger perspective, quite interesting to focus on, if it's not already there, of course.
Yeah, I agree. So this is Leila, by the way. I think for our project, the really interesting part while we were working through it was looking at how the vulnerability index or the median income played a role. And this was, of course, a proxy because we used census data. So we assumed that the ridership was from the areas surrounding the bus routes. But if you could have data that was directly from riders, from like a survey or something, that would be even more powerful and probably more telling. So, because for example, for us, census data only looks at the residents, but if you know that there are a number of high-paying jobs along your route, but it's lower income residents, like that could be a limitation that we couldn't figure out just from census data. And so I think that absolutely getting a better picture of the ridership and the clients would be amazing and is very important for improving service.
Yeah, and this is Nick here. One interesting analysis that I saw recently came from Transit Center, and some folks there actually used the loads employment data to try to look at where essential workers were most heavily concentrated and what those origin destination pairs would be, so that transit agencies could try to focus some of their flexible service in those regions. So that's just another example of how you might use some different data sources in order to take a look at some of these interesting characteristics of the ridership.
And I'll follow up because I might have missed it, but I'm wondering if any of the presentations today, so the title is, what is it? It's, well, okay, it doesn't matter, but I'm thinking about the user experience. And, you know, we're still kind of talking about OD pairs and the performance of, say, complete trips that include transfers and assumed or observed routes, actual routes taken by passengers. I'm wondering if any of these presentations or people on the call have used kind of long-term smart card data to understand the performance experienced by actual users as indicated on the trips taken by a user, either, you know, based on a longitudinal, a long-term record of smart card data for a user and matching that against the performance they actually experienced over the course of, say, a month or a year or their lifetime.
Menno here, Steve. So we did, to a certain extent, we had a nice collaboration with WMATA also last year, where we had access to a year-long data from both passengers and train data. So that did allow us to show a bit more about, say, developments over time. So to a certain extent, yes, although I fully agree that I think we should do more there. I think one of the things we typically run into is some privacy issues with having the same smart card ID over time, that you should not always track people in that level of detail. So sometimes we run into that, but yeah, I think it would be very interesting to do more into.
And Mark, I see your comment, and I've actually included you as a panelist. So if you'd like to unmute and expand on that, it would be great to hear.
I was only going to add that in Tianwei's work, he was looking actually at people's experience before they actually took a satisfaction survey and whether their overall experience over the last month or 2 months had actually influenced their overall satisfaction. So, and what he discovered, interestingly, was that actually had a significant influence on their overall levels of satisfaction with a specific trip. So they did have this sort of memory of their previous trip experience when they were thinking about their specific trip they were asked about.
Okay, thanks for repointing that out. And there was a question about whether or not the video will be available, and I saw for that presentation, and I saw that it's also in the Google Doc. So hopefully there's a chance to maybe drop a URL for that presentation or something like that as well, Mark.
Yeah, I dropped the URL out on the Google Doc.
Okay, awesome. Thank you so much. So I think that concludes this session. Thanks to all of our presenters for the really great presentations. I think I'm really enthused to see all of this great work about user-centered measurements of performance. I'm very excited to see the potential, just, you know, selfishly for my own research interests, interested to see this take on more and more of a role in thinking about equity and justice in the delivery of services and the experiences of riders, at least some of those dimensions. So loving seeing that blossom here, and look forward to catching up and following on all of these great research threads. So thanks so much, and we'll see you after the lunch break this afternoon.